So I'm Brian Ingram. As Max mentioned, I'm at Argonne National Laboratory just outside of Chicago, Illinois in the United States. I have been involved with magnesium battery and multivalent batteries in general for 6 or 7 years now. And so I'm really excited to show you kind of where I think, and this is the first speaker of this meeting, kind of where I think magnesium is, specifically magnesium, and to start the conversation for the next 3 days, and then to show some of the highlights of where we've progressed at Argonne in our own research. So here's just sort of a slide we put up all the time, but obviously energy storage is really important for all of our needs, and so we need to move beyond lithium-ion for many different applications, and so that's what part of this meeting is about, is one aspect of moving beyond lithium-ion. Before I forget, I just want to put up, this is the sort of the JCESR, Joint Center for Energy Storage Research team. It's multiple different institutions in the US and in Canada. And so these are all the different names who have somehow contributed or touched the topics I will discuss today. Those in red are people who were directly involved with some of the data that I'm putting up today. So this obviously could not have happened without everybody involved. Okay. So, obviously in this meeting, we all know some of this, but I wanted to put some of these thoughts up, as I said, to be a springboard for the next 3 days. As the first speaker, I feel like I have that opportunity. These are all, numbers for comparing lithium, magnesium, calcium, and zinc, and looking at the opportunities that moving to multivalent presents us. From abundance and cost value, we can see that magnesium is lower cost and higher abundance, which is great. And then if we look at the energy densities, obviously if we consider energy densities, or I guess I plotted this capacity, magnesium gives us a great opportunity, as does zinc. Obviously lithium is real hard to beat on the weight category. So. And then, of course, these numbers are somewhat debatable. I mean, we can put big brackets on them, but I think they show the trends of why from a very high level, we are where we are, and why we want to follow up on zinc. So if we dig a little bit deeper, these are some technoeconomic models that we've been running and updating as we go. And so we can see here on the left, these are pack-specific energy and pack energy densities. So once again, we can debate these numbers and where they really should lie, but this shows at least a good trend of a pack at a pack level. And so these three bubbles represent three different types of cathodes: metal sulfides, layer metal oxides, and dense metal oxides against magnesium metal. And then that's sort of a comparison to a lithium-ion system. So you can see that if we get everything to work, if this group here solves all the problems, magnesium can be competitive with lithium. It's a big if, though, right? And then on the right, I'm looking at the cell level or the materials level analysis, and the cathode-specific capacity and the cell energy density at the cell level. And you can see these are sort of assuming different voltages, there's different chemistries, and you can see that if we want to get to that sort of transformative energy level, as I've somewhat arbitrarily defined, but nonetheless, if we look around, if we say we're limited to about 300 milliamp hours per gram, which would be a reasonable statement, we really need to get, this picture really shows us that the higher voltages allow us to get there. Is a more direct way of getting to transformative energy densities, if that's your primary parameter of success. So one more way to think about this is if we look at the average voltage of the magnesium cathode versus the magnesium metal. And then we look at the cell, once again, the cell level capacity, and we look at the sort of the energy levels there in the dashed lines. We can see that these circles represent different cathode materials. The size of the circle is proportional to the calculated, computationally derived migration. So larger cells theoretically have higher magnesium transport properties. I put on some lithium compounds just as a comparative. And you can see once again that we can sort of highlight in this model, this picture, drives some of the research that we did at JCESR and at Argonne. So we want to move to the top right of that graph, obviously. And then the next step is commenting, well, if you want to get to the top right of the graph, you really need to have an electrolyte that allows that. So today, I will not be talking much about our electrolyte work, but there's some really great talks today that are highlighting some different aspects of electrolytes, ensuring that we have high Coulombic efficiency against the metal at the low voltage window as well. So there's a lot of great opportunities to explore those topics. And then the last, here is just a similar laying over top calcium and zinc in that same space. So you can see where the advantages of calcium and zinc are on this plot relative to magnesium. Okay, so obviously because we're still working as a community on high voltage electrolytes, investigating cathodes because everything is interlinked is a challenge. So we have really, and I think the community has really spent a lot of time in understanding how can we verify electrochemical activity of magnesium or the other multivalents in the cathodes. If you don't have a working, or you have an electrolyte that is not 100% efficient at high voltages. So, there's been a lot of materials characterization, which makes this effort as a material scientist, of which I'm a material scientist, has really made this a fantastic problem to consider. And so that's just sort of, so I've really enjoyed the last 6 years looking at these materials. So that's kind of a picture of where I think the pros and cons of magnesium are. I think it highlights some of the particular challenges that are clearly being discussed the next 3 days. And I'm pretty excited to physically be here and engage in the conversations with you all on in these areas. I'm going to move on to the work that we did in JCESR and at Argonne. And one of the areas that we looked at was this space here in the oxide spinels. They are, as we see them, enable a higher voltage and a higher energy density for magnesium. And so that's why we spent a lot of time in this area understanding it. As we saw it, it was one of the best paths to achieving high energy density magnesium ion batteries, as that was our definition of a success. Like, we were looking at magnesium specifically for achieving higher energy densities, or with higher energy densities. So an overview of slides or data that I've presented at this meeting in previous years, but just sort of the progression of where we started. And it was a computationally guided effort where we examined a series of different materials. This is spinel data, and we looked at migration energies as we screened over many materials. And this work was done at the Lawrence Berkeley National Lab with Gerd Ceder's group in collaboration with us. And we identified design principles and materials that allowed for high energy density, high mobility of magnesiums. And then once we did that screening, we moved on to diffusion studies to verify that the magnesium computational work was what it said it was, and we accomplished that. You can see that we're comparing a couple different experimental approaches to that of the computationally derived migration energies, and it's consistent for these 3 spinels, as I'm showing. And then we eventually moved on. Once we identified and verified the migration energies, we actually showed some electrochemistry, and on the far right, I showed this is NMR data, which is site and element specific. And we can see we moved from a pristine magnesium chromium oxide spinel, where we can see a peak that corresponds to magnesium in the tetrahedral sites. And then we do a constant current or constant current voltage charge step. And we can see that the magnesium content in the tetrahedral sites of the spinel decreases. And also there's a shift, which is consistent with the oxidation state. So this was pretty exciting work. We showed that we did have electrochemical extraction of magnesium at, and I believe this was held at roughly 4.3 volts versus magnesium, which is extremely high. So we know we were burning through electrolytes, and there were a lot of other issues associated with this. But this was solid-state specific investigations showing that we were able to extract magnesium. So this was all done a while ago, and we were really excited by that. So we continued to work in this space. And we had published papers in the chromium system. We looked at the vanadium analog system that has lower the electrochemical voltage, so we don't have to operate at 4.3 volts. We could go a little bit lower. We maintain magnesium mobility, but vanadium was really complicated because a lot of rearrangements, multi-phase systems, phase segregation were all observed. So then we moved on to solid solutions within this sort of phase space. And this is a paper we did on a chromium manganese, so magnesium, chromium manganese oxide spinel. And we showed that, in fact, we were able to do some reversible electrochemistry with this material. So now we're pretty excited about where we're going with this program and progressing with it. But there were big questions that remain. I mean, it's not, if we had been successful, 100% successful, right, we would have a magnesium battery on the shelves, right? So in this system, one of the areas is once again, I'm putting aside the issue that the electrolytes are imperfect. So there's still electrolyte decomposition and interphase deposition that we don't want to see, which we are working on within this program. But I'm focused very much on the cathode right now, specifically. But we see that there's a large voltage hysteresis and a fairly significant capacity fade in these materials. So we asked the question of why is that? Can we understand that better at a materials level? And so one of the ways we attacked this problem was we looked at an operando measurement where we went to the advanced photon source at Argon, our synchrotron source, and we monitored the magnesium manganese chromium oxide in operando in an operating cell. Initially, we looked at a combined neutron and X-ray refinement to understand where all of the cations were situated and all the structural information of this material. And so now we have some really, from this sort of baseline material, pristine material, we are able to answer the questions of which cations are active, how much magnesium is actually being removed, how reversible is it in reality, and then ultimately getting to, from the cathode contribution towards hysteresis, what is the nature of that hysteresis. And so here is some information on the experiment. And you can see that we have an operating, a full operating cell that we align in the beam parallel with the beam. So you can see here that we are actually aligning, and it's showing a little bit of an angle here, but we can align with the beam direction, the cathode spacer and anode. So we can look at each layer individually, and as we've progressed through this effort here, we were actually able to do a depth measurement across that. So we can look at the top and the bottom of the electrodes as well. So here is the data as collected, and I think this is only showing 1 out of every 10 scans or 1 out of every 8 scans. Don't hold me into that, but this is essentially the data. This is the voltage data as we charge and discharge, and then here's the collected data. Obviously, that's hard to look at. We can sort of see movement of peaks, but then we went ahead and analyzed, and we did Rietveld along each one of those points. It would be great to be able to do that automated, but it ultimately was fairly by hand, which is our postdoc at the time, Liang, was really patient with doing this. So here we can see the voltage, obviously, that's easy to measure. We were able to get lattice parameters, cation occupancies, and some changes in geometry as a function of the voltage. And so I'm going to look a little bit closer. So during the first charge, we go from, and this was done against a carbon capacitive counter electrode. So this is not against magnesium metal. So we were bypassing the challenges associated with magnesium metal, and we were using a carbon capacitive counter electrode. So we can charge the system. We can see that there's a clear decrease in the lattice parameter. And so this column here is the magnesium content and tetrahedral sites of the spinel, which is their normally occupied sites. And this is the magnesium content of the normally unoccupied octahedral site. So the octahedral site that is between the two tetrahedral sites. And you can see that there's extraction of magnesium from its normal site. There's a little bit of insertion into the normally unoccupied site, but net there's magnesium loss, which is what we want to see. So we verify the magnesium cations are actually removed from the lattice. There is also a redistribution of the magnesium, and we get about 0.12. So only that's what we would expect from the voltage as well. And that is consistent with some of the measurements we had, computational measurements that shows that as we extract magnesium from the tetrahedral sites, we actually favor the existence of the manganese also. Oops, sorry, wrong button. The manganese also begins to favor, and I'm not showing the data here, the manganese also begins to invert a little bit onto the normally octahedral sites. So we see a nice rearrangement, but ultimately an electrochemical extraction in real time of the magnesium. Then we begin a discharge step, and we can see that this initial part of the discharge step actually returns the material basically to its pristine state, which is wonderful. That's what we want to see, a topotactic reaction. So we get the magnesium reinserted. The cations in the normally unoccupied octahedral sites migrate back to the tetrahedral sites. And so at this point, the reaction is highly reversible. However, if you continue to discharge, it's very easy to do so. We begin to over-magnesiate the system. Cations migrate from those tetrahedral sites back into the normally unoccupied octahedral sites. We see a large expansion of the normally octahedral sites by further reduction of the manganese. And we end up forming a disordered rock salt-like structure. This is consistent with other reports in the literature and certainly can be cycled to some extent, but this is not the approach that we were going for. So we now have a much better understanding of what the over-magnesiation does to the structure. And then upon ultimately a partial but second charge step, we are still able, even beyond this over-magnesiation, we're still able to electrochemically remove magnesium from the lattice. We're starting from a different starting state, right? We're starting from an over-magnesiated state. So, and then there is irreversible manganese migration onto the normally unoccupied octahedral sites. So this ultimately becomes a source of the hysteresis and overpotential, because we've fundamentally altered the initial material, the starting material, by over-magnesiating it. And so, in summary of this section of the work, we can see that we've plotted the vacancies on, or I'm sorry, the 16th site, which are 100% vacant to start with. The green is the magnesium, and the purple is the manganese content of the tetrahedral sites. And we sort of show, we propose a model that this movement of magnesium through the tetrahedral into the normally unoccupied octahedral site facilitates extraction through the charge. As we discharge the initial, we actually see the reverse state where that moving it through the unoccupied octahedral site facilitates motion. And then ultimately, over-magnesiation pushes manganese and magnesium into the normally unoccupied octahedral sites. All right. So we have it, and this excess and this movement contributes, as I said, to the overpotential as well as to the hysteresis in the electrochemistry. I say contributes because obviously there are other contributors too, and that a lot has to do with electrolyte stability and reactions and conversion. So that brings us to the next question of the solid state transport of magnesium in this material. And so we wanted to measure it directly, not just electrocemically, like we would normally do with like a lithium ion. We could do a GIT experiment or something like that. Well, we know that because of the electrolyte challenges, that presents a very difficult technique in magnesium. So we went ahead, and my background is an electroceramic person. I said, well, why don't we just measure it directly without electrolyte? We just make a dense pellet and begin to look at the direct measurements. We could do some solid state impedance, for example, or and it turns out that it was rather challenging in this material, but we were able then we settled on conductivity relaxation studies using platinum current collectors. So in principle, magnesium blocking electrodes. This is a picture of the schematic of our setup, our measurement setup. The pellets were about 98 to 99% dense, and I think that the grain sizes were approximately 6 to 7 microns. We tried a couple experiments where we actually did multiple different grain sizes and saw no difference in the data. So in principle, if you have an electronic conductor with this setup, you really should not see a relaxation of the current with time. But the data look like this. This is the raw data, collected about 3 data points per second. So there's a lot of data. The spread you actually see are outliers. There are only a handful of outlier points. Most of the data runs right on that line. By traditional or conventional modeling, we would expect to see a relaxation that would look something more akin to this dashed line. But we see a very different picture, and we were not able in any conventional manner to model the data as we observed it. This is repeatable across multiple thicknesses, temperatures, and different polarizations. So we see a very consistent picture with all of the data we collected that did not match any of the conventional interpretations. So we then began to think, well, is there a more generalized picture that we could, theory that we could propose that would explain our data? And so we moved away from the conventional Nernst-Einstein relationships that assumes rather independent behavior of the charged species and looked at the Stefan-Maxwell diffusivities. And we built a model that fits the data very nicely. And come on, there we go. So we call it the extended or extended mixed ionic electronic conduction model, which is a more generalized approach. Many people do it in liquid systems, and we were applying it to a solid system. It does reduce down to the more conventional picture when you move towards a more dilute space where you have less magnesium or conducting species, I should say more generally. And so that's good. So it does reduce down to the Nernst-Einstein relationship in a dilute case. And so here's a picture of, on the left, 4 different polarizations of data, fit with the data, and then using the model to fit them. And on the right is an example, actually all combined, all those 4 polarizations upon relaxation. So we looked at both the polarization relaxation, sorry, that's using the same word twice. And then, so as we polarize it, watching the relaxation, and then as we remove the polarization back to 0 volts, and then watching it relax back to equilibrium. And we were able then to look using an error analysis approach. We were numerically solved for these 5 parameters, 2 of which were related to interfacial features, and then the 3 that were bulk parameters of which we're interested in, the conductivity, the chemical diffusivity, and Newman's number, which is related to the transference number, so the amount of ionic to electronic ratio. And then if we did this at multiple different temperatures, we can extract back to room temperature, and on this plot, it's back to the 0 point. We're able to extrapolate to room temperature to get a conduction value and an overall total conductivity value and a chemical diffusivity value. If we take these, so I plotted the 3 bulk parameters here as a function of pellet thickness. These values actually are, the variation you see here is much less than that at different temperatures. So there is some variability here, but ultimately, because these are geometrically normalized values, that we shouldn't see too much change at different thicknesses. This ruled out either contributions from interfacial events as well as ultimately other non-bulk issues. Because the variability we see here is very much smaller than the temperature variations on the properties. So we believe these are the true bulk properties that we're extracting. And if we plot that on a plot here on the right, which is the total conductivity on the y-axis and the chemical diffusivity on the x-axis, that's about where this material lies. And if we compare that to some very well-known lithium systems, we see something that's very interesting. The diffusivity, the chemical diffusivity, is actually not that out of line with what we would expect from lithium ion. And that's consistent with our computational measurements. It's consistent with our earlier experimental diffusivity measurements. But this particular material has very poor total conductivity. And that's the real limiting factor that we believe is the issue here with this material. Magnesium ion transport is actually limited by the total conductivity and not by diffusivity. And so that interaction between electrons and ions in this material becomes pivotal in understanding how to design it. So our next step is, and we've looked at other spinels that we've increased the conductivity, and we in preliminary work, which I don't have here, we do see an improved net performance. But I think the other challenge, which I'm not, the other assumption here, is that we don't have conversion reactions and we don't have other other parasitic reactions at surfaces, which is another problem that's external to the bulk measurements. But what are some other implications? Well, if we wanted to understand how to design a material, with the lithium ion, we clearly have a good understanding. There's been 35 years of engineering lithium ion electrodes, right? So we propose the implication of understanding the mechanism of transport in magnesium spinels is that indeed you can't design the same type of an electrolyte or electrode design as you would with lithium ion. And so one of the areas that we're currently very interested in is how best to approach that this is at a particle scale. You can see the blue here is the modeled graphite contact points, so how much graphite or carbon you would put into the electrode design. And so we began to look at how you would design that relative to lithium ion to take advantage of reasonable diffusivity and low conduction. We modeled some impedance data, and essentially the take-home message here is this is you can see that we break the line here. So at lithium, we have a relatively low impedance. We see some diffusion nature of the impedance before we move into this point here. But in magnesium, we actually see it's 10 to the fourth. And then we see this, and then there's just a small amount of extra resistance on top of this 10 to the fourth, so 2, 4, 6 ohms. So what we believe to think is that under identical geometries and interfacial properties and coverage, that this high frequency intercept, either very high or very low, is a relationship of the resistance of the particle to the total conductivity of the electrode, which would be the composite value. We don't see a diffusion tail in the magnesium case, but we do see it in the lithium. And that charge transfer, which would be the arc here that we see, we propose, seems to be depend on the bulk transport. So we modeled the interfacial values to be the same. We just set them to be the same. But you can see this charge transfer arc here and here are very different. And that the only thing that's changed between these two models is the bulk transport. So we think that we need to make use of a more optimal design around utilizing the graphite and using smaller particles to take advantage, to mitigate the loss or mitigate the low conductivity of magnesium relative to lithium. And then ultimately, we'll need to pay a lot of attention to what the actual interfacial properties are. We know that they're probably lower in the magnesium case than lithium. So, and then we did some further modeling, and I want to leave us some time to have a conversation. So ultimately, under lithium, if I were to unravel this like a globe and look at the map of the carbon coverage, and we take this slice here through the particle, and we plot the voltage through the interior of the particle for an NMC material, and then this would be the current on the exterior, so you can see most of the current is moving through and near the triple phase boundaries with the graphite. But if we look at the magnesium case, we actually see a much less, I don't know why, oops, sorry. Oh, well, it's just stuck there. We actually see a lot less activity through the bulk of the powder. We see a much more isolated current at the triple phase boundaries. And so it's much more localized than the magnesium case. So that points to another aspect of a better electrode engineering ultimately with magnesium versus lithium. Better, that's not correct. Different electrode engineering for magnesium specifically relative to lithium. So I'll leave the conclusions up, but I'd rather open it up to questions and conversation. These are relatively readable, so, and just a repeat of what I've said throughout the talk. So, thank you.